settle in for a minute. Just take the next minute to do nothing. Literally nothing. Absolute radical act in this world. No production. No goals. Not even trying to meditate. What is it like to just be here with no expectation? Find yourself fixated on something. Notice what it's like to have that tension. And then see if you can just relax and let it go away. Just like unclasping your hand. Before we end, just take a minute to wish yourself well. Just talk to yourself like you were a good friend. Wish yourself happiness. May you be happy. You deserve love. You deserve happiness. Let's do some calculus. All right. So I tossed an offer out. Oh, hi. So you better?
A little, yeah, still bleeding. I don't know.
Good. I was getting worried about you.
I lost half a cup of blood, man.
Good Lord.
Yeah, it was a lot of blood.
Jeez.
Not better now, I think.
Good. So I made the offer to extend the web work. No one took me up on that. Is that still like, do you need more time? Yeah, okay. I'll extend it a bit. I'm not gonna pop a new one out yet, so a little reprieve. Just a few days without web work. Couldn't hurt anybody. Let's pick it back up where we, kind of an example that we talked about. It is an example we talked about on Monday, but I want to hit it from a different angle again, because this is something we kind of understand. It's a nice polynomial. We've done all the work. The only work we really didn't, I guess we even did this. We cranked this out. So remember, the goal here is to find any possible maximums and minimums. Local maxima and minima. So in other words, local max, local min, little bumps, like that. Step one in this process, just crank out the first two derivatives. You're gonna be really happy if you just do that, because you're gonna use this to find our critical values. So remember this first derivative, wherever it's 0 or undefined, is a critical value. This thing, we factored it out. We found that it is 0 when x is -3 and 2. So those are my critical values, and I marked those on a number line. And I'm going to recommend to you to create two number lines. one for the first derivative information and one for the second derivative information. So here I just put out this line and I plugged off, just marked off these two critical values. We don't know if they're maxes or mins yet. That's where the second derivative info comes in. So let's talk more about the second derivative. The second derivative is the source of information for concavity. It tells us what the general shape of the curve is like. This is f double prime is negative, and this is f double prime is positive. And if f double prime is 0, and I think Alex mentioned something like that, then it's straight. It's essentially flat at that point. Very little curvature. So we can use the second derivative on its own to understand the curvature and how it changes. So let's make a little bit of plan here. So step one is use f prime to find the critical values. Step two is to use f double prime to find concavity and inflection points. So an inflection point is just a place where I change from concave down to concave up, or vice versa. So inflection point means a change from this to this, or from this to this. You hear people say inflection point all the time in the news. When they're talking about some critical situation, they say, we've reached an inflection point. At least I've heard that like all over the place. I try to avoid the news as much as possible, but this is something you hear. And what it means is the rate of growth has changed dramatically. So imagine if you had maybe cost here and a number of units produced or something like that. This is a very businessy example, especially for a guy like me. But say that the growth change was like this for a while, and then at some critical production rate, this is like units produced here, at some critical production rate, suddenly the cost starts to change in a different way. Notice here that the cost is changing faster than the cost is changing here on a side-by-side basis. So if you go here, you see your cost didn't go quite up as much, or your cost goes up faster here than it goes up over there. The alternative would be something like this. Cost is rocketing, or starting to slow down, and then suddenly shooting up over here. So that is an inflection point. Both these are inflection points. And they indicate a qualitative change in the growth rate. That's an essential way a nice simple way to think of what an inflection point is. So let me actually write that up here. This is a qualitative change in the growth rate. Okay, so how do we do this? Well, it's a lot like the critical values. So part one here is find f double prime. We'll assume that's done. But find where f double prime of x equals 0 or is undefined. Just like the first derivative stuff, just like critical values. And then analyze the sign, SIGN, of f double prime in the regions created by these points. So B is analyze the sign of f double prime of x in the resulting regions. So this would be between places where f double prime equals 0 or is undefined. So let me let you get, I'm going to come over here and do this as an example with our friend from yesterday to make this clear. examples. So in this thing here, first off, notice that f double prime is not a fraction, so it can't be undefined. There's nothing weird going on with it. There's no division by 0 possible. So f double prime of x will be defined everywhere here because it's a polynomial. It's just 12x plus 6. There's nothing you can't multiply by 12 and add 6 to. But it could equal 0. So set f double prime of x equal to 0 and solve. And what I'm going to get here is 12x plus 6 equals 0. And you could solve that probably in your head to see that x is negative a half. Make sure that that all looks legit. Well, I'm just going to camp here for a bit because I see people still looking at the right side of the board. So let's take a little break. See, folks looking at the left side, that's good. That's a plus. So we're going to take that second derivative, set it equal to 0. From that, we get x is negative a half. So that's where the second derivative dies out. I'm going to indicate that right underneath this f prime line, and I'm going to do it in a way that keeps things kind of aligned. So this is still 0 down here. And this looks like maybe a negative a half right there. So now let's finish this up. I'm going to test f double prime in each of these regions. So here I'm going to test x equals negative 10 because it's way in here. So f double prime of negative 10. Can you see that that's negative? Does that look right? Yeah? And then f double prime, I'll pick some point out here. I'm going to test 10. F double prime of 10, is that positive or negative?
Positive.
Positive, thank you. It's like 126, right? So in this region, to the left of negative 1/2, we are concave down. To the right of it, we are concave up. So I'm going to put a little thing here that indicates that for me. That's the concavity information. To the left of this point, it's always opening down. To the right of it, it's always opening up. And we did this analysis last time, but let's do it again really quickly. So I'm going to test the first derivative in each of these regions. So here I'm going to test x equals negative 10. Because it's clearly in this region here. How does that work? So I've got 6 times a negative times a negative. This is going to be positive. F double prime is positive here. That means I'm increasing on this side. In this region here, I'm going to test x equals 0. F prime of 0 in this region is going to be positive, positive, negative, so less than 0. So when I say that first positive, I'm looking at this. Positive, when x is 0, this is positive. When x is 0, this is negative. So the result is negative. And then finally, f prime out here, I'm going to test x equals 10. I see that I've got positive, positive, positive. So out here, I'm increasing. So look at this. We are increasing, decreasing, increasing. And now I just got to put all that information together. So step 1 in understanding a function, especially if you're going to graph it, is this process here. Then step 2 is to put those 2 pieces of information together and make a pretty graph. So let's do this. Let's get a few points as anchors. So that we actually know where the thing is. It's not just floating in the plane randomly about. So f of 0 is 2. That helps. Cool. There's a point on the graph. Good to go. And I think we actually found the output values at 2 and -3 last time. Didn't we? Something they were horrible, like big values. What was f of 2 last time?
I will calculate that.
Thank you. Right, and f of -3 as well. Let's just get those 2 points because those are actually important. They're where maxima and minima occur.
F of 2 is -42.
-42? Good Lord. I remember it was atrocious, so that sounds right. What about f of -3?
I think that was -30.
-30? So I regret my unit choice here just a little bit, because if that's 2, I'm not going to get this graph on the board. It's going to be on the roof of Loyola. So let's back that down a little bit. Here's how I would do. They're both negative, huh?
Yeah, I don't. I got -26 because that's 16 times 2, so it's 32 plus 12. That's 44.
It's -42 and +29.
Oh, positive. Okay. Positive what?
For -3, it's +29.
+29. Let's just check this shit out. We got some serious disagreements here. So f of 2, that's going to be 72 plus 2. That totally looks like -42. So that sounds good. And then -3 is going to be, good Lord. What did you get, Callie?
The final answer was +29.
+29. And Olivia, what were you? You got the -30.
I might have written this down wrong, but I got +29 whenever you plug in +3. But I don't, that could be wrong.
Oh, +3. Yeah, that sounds right. But we want -3.
I don't know. I
It's okay. It's okay. Yeah. So let's do it. Let's just do this. So this is 2 times -27 plus 3 times 9 plus 36 times 3. I think that's 108 plus 2. That looks positive to me, definitely. Kelly, what was that? Sorry, one more time.
+29.
Can someone give us a sanity check on that, please?
That's right.
That's right. Okay, cool. Thanks. Okay, cool. I was hoping they weren't both negative. That would have been like, just sucked, kind of. So at 2, wait, let me fix this up over here then. +29. So at 2, we're at -42. 1, 2. Let me show you how I would just hack this. I'm going to make that -42, and I'm just going to work everything else from that. So that point is going to be this point here, and it's a minimum. Notice how the second derivative info is totally in sync with what we expect. That looks like a minimum. That looks like a minimum. That looks like a maximum at -3. The curvature, concavity, looks like a maximum. So let's see, it's -2, 3. Then we go up to +29, which is like 3/4 of that distance. You know, again, not brain surgery going on here, so we can just wing it. So we've got that max, and then we know that 2 is a point we go through. So that's like here, sure. There's 2. That's another point on the graph. So we got a bunch of points on the graph. We're good. We could theoretically find where it intersects the x-axis by setting it equal to 0 and solving. That doesn't actually look like a fun thing to do. I don't think that's going to work out real good for us. So, putting this information together, step 1, make a rough sketch based on the first derivative info. So what I mean by that is this. And I'm making it in dotted lines. So notice I go up there, I go down there, and then I go back up. Rough sketch, just to get the increase, decrease data incorporated into the picture. Now I can tweak it, and I'm gonna be really good and subtle about this. Notice that exactly at -1/2 is where it changes from concave down to concave up. So that means if this is -1/2 right here, that right at this point on the graph, it changes from concave down to concave up. And that actually gives us a lovely bit of detail on this. So there's concave down, then all of a sudden it becomes concave up. Now because my scale sucks so bad, this is, oh my God.
Just draw an arrow and say concave up.
Yeah, no shit. Yeah, I'm gonna totally wing it, and then I'm gonna make it, that intersected it too, if you can believe it. It's just so hard to see. And then concave up. There we go. But the inflection point is right there. So because my units are all screwed up, this makes this thing challenging. Not a bad picture. I got one for you. Bless you. Is that someone in here? Yeah, that was yours. Okay, cool. I was like, is that coming from my head? The next room? Who knows? All right, your turn. What I would like you to do is repeat this process, my friends, for the following function. So I'm gonna cheese out here, and I'm not gonna give you F. What I want is the critical values and possible inflection points. So suppose f prime equals 3x to the 4th minus 9x squared. So step 1 is find critical values. Step 2 is find inflection points, if there are any. And then step 3 is classify the critical values as max, min, neither. So remember, that's your, you do need to take one derivative here to get f prime, f double prime. That's it. I'm trying to warm us up on the solving equations, because you know that's a stressful area for some. on cruising. Keep on cruising. Look at where each of those pieces is 0 now. You got a product down on, look where each piece goes to 0. Still, pull it. Okay, all right. Oh, this is going real good. And so, the only little tip I would have is when you're the one taking the screw, put a plus minus. And that's great. Oh, good walk. Joey, how's it going? Okay, good. Good stuff. Who knows about it? Yeah. Geez, I think it's, yeah, it's. So now, this is going to equal 0 where each of these two pieces equals 0. Same down here, so you can kind of pull it apart into two different equations, right? Does that make sense? Sure. Okay, all right.
Yeah.
Okay, yeah, let's see.
0. Where?
So either 6x is 0 or 2x squared minus 3 is 0. Does that make sense?
Yeah.
Yeah, and then that makes the problem really simple. Then you just have to solve where does 2x squared minus 3 equal 0?
Oh,
Yeah,
yeah.
and then you do the same thing. Okay, yeah, that's, I think you're not alone. Yeah, but I mean, here, we can talk just a little bit. So in this one, this is gonna equal 0 when each of the pieces is equal to 0, but you have a product. So you make your life easier, like, okay, either 6x equals 0, which is easy, because that just means x is 0, or this piece is 0. So in other words, I write that out, then 2x squared minus 3 equals 0, and solve that. So breaking it down into little pieces, but you can whatever you feel happiest with. How are we doing here? Yeah, that looks solid. Yeah, you are on the road. We got one too many x's. So which one you factor? Yeah, so there should be an x on that. If you pull the x out front, make sure to not have the x there. Yeah. And then, so now look, for this product equals 0, either 6x equals 0 or 2x squared minus 3 equals 0. And I make that into a new equation. Just like that, yeah, it'll be much simpler. Much simpler than what you got it correct. Yeah, 3 times. So just remember this, when you're the one who takes the square root, plus or minus goes in front. Yeah, yep, class, ooh, sorry about that one.
So we have those critical values.
Nice.
And then in here, and then that double prime, there's not that as my point.
And there's one more, because this can also equal 0. Oh wait, that's,
This is F double prime.
yeah.
This is F prime.
Yeah, your factorization here is a little weird, but man, I love that. That would actually be square root of 3, not 1.5.
Square root of 3.
Yeah, because 1.5 times 1.5 isn't 3.
Oh.
It's 2.25 or something like
Yeah,
that.
let's say something. 1.5 times 2.
Yeah, so that would actually be square root of 3, and just use that symbol. Yeah.
So root of 3 on both sides?
Yeah.
But just positive and negative?
Yes, sir. Yeah.
Okay.
But good thinking. How we doing? Oh my God, that's beautiful. Oh my God, wait, I just want to look. Can you back it out? I just want to look at your graph again. Holy shit. Okay. This is so nice. This looks great. So only one little tip. You're not the only one missing it. You should put a plus or minus when you're the square rooter. Yeah. You're welcome. Okay, let's go. Let's hit this up. So I'm going to find out where this, first off, I look at this and realize there can't be any division by 0. So this is defined everywhere. There's no fraction, so there's no trouble like that. There's only, can it be 0? So I'm going to set this equal to 0. Now look, I've got a product. When you have a product of things equal 0, that's what you're happy, because that means you can break it into 2 problems. If a product of things equals 0, each piece could be dead. So this becomes either 3x squared equals 0 or x squared minus 3 equals 0. And I've seen some interesting things happening on this one. This one's straight up. This is just x equals 0. But this one, the way I would solve this, and I saw a couple routes. So here's what, I'll show you what Alex was doing. He factored the left, which is really lovely and a very sophisticated way to do it. You just gotta make sure you do it right. That's the difference of two squares, but the thing that's squared is the square root of 3. So from that, you could get x equals positive square root of 3 or negative square root of 3. The other way, there's actually two more ways. The other way is you move that 3 to the right, and then you take the square root. Don't forget that when you're the one taking the square root, you've got to account for positives and negatives as a possibility. So notice how we got the same thing either way. One last way. Worst, the way everybody moans about. I heard it. I know what you think. I know you don't like this, but it'll save you sometimes. So notice that up there, we have a equals 1, b equals 0, because there's no x term, c equals negative 3. So x equals b, negative b, plus or minus square root of b squared, 0, minus 4 times a times c, so that becomes plus 12 over 2a. Now you gotta find square root of 12, which is 2 square root of 3 over 2, and we get our friends. 3 different ways to do that. Can I answer any questions about getting those critical values? Because we've got 3 of them, right? We have 3 critical values. So if I look at f prime, 0 is a critical value, root 3 is a critical value, and negative root 3 is a critical value. I'm going to have 1, 2, 3, 4 regions to test. Let's just do the testing before we even get to the second derivative. So we can probably classify these without the second derivative info by using the first derivative test that we talked about. Let's do this. So here, so f prime, and I would leave this in its factored form. Its factored form is, oh, check it out. Hell, we'll just do this. Why not? That'll work great. Because all we care about is positive, negatives. We don't care about exact values for this. Yes, Juan, sir.
A question. So when you first put x squared minus 3 equals 0,
Yes.
are you missing a 2, or where does that 2?
That'll come in here. So this is from the first part. This is just the first derivative.
Okay.
The 2 will kick in when we get this part. That's on the second derivative.
Oh, okay, got it. Yeah.
But yeah, good call. We'll get to that very soon. Other questions or concerns? Okay, let's test. So I'm going to test, you should know square root of 3 is like, it's less than 2 and more than 1, but it's about 1.7. Good things to know. So I'm going to test something that's clearly in this region. X is negative 10. Look at the first derivative. 3 times something squared. That's positive. So f prime is a positive times, if I take 10 and negative 10 and squared, I get 100 minus 3, that's a positive. So this is positive here. Look how easy that is. Here, low-hanging fruit. What's the low-hanging fruit in this region?
-1.
Beautiful, -1. So lovely. We don't get to test 0 because it's one of our critical values, so we'll go for the next lowest fruits. So let's see here, f prime is going to be positive. That first part's always positive. And then I've got -1 squared is positive 1 minus 3 is negative. So we're less than 0 here. And here I'm going to test x equals +1. Do you see it's the same damn thing? Because everything's squared. So this, we have f prime is a positive times a negative. That is a negative. Aha. And then finally out here, I'm going to test x equals 10. That gives me the same shit I had over here, because everything's squared, so positive times a positive. Positive. So now I understand this function. It goes up, it's there, goes down, keeps going down. Might level off a little bit, but it keeps going down, and then out here it goes up. So, relative max at negative root 3, relative min at positive root 3. We know that much right off the bat. So let's just summarize what we know so far. We have a relative max at x equals negative root 3, and a relative min at x equals positive root 3. And now let's do some inflection stuff. And that's all down here in the second derivative land. So, before I go on, any questions over what just happened? Good? Do that? That's pretty straightforward, right? One of the things I'll do on the, oh shit, the next exam's all online for the most part. I don't know what I'm going to do on that. Ignore that I just started that sentence, please. Back up. We do this again. So let's find where f double prime equals 0. Let's set that equal to 0. Setting that equal to 0, and I'm solving, and I have a product. So either x equals 0, or 2x squared minus 3 equals 0. Again, a plethora of ways to solve this, but I like this one. 2x squared equals 3, x squared equals 3 halves, and now take the square root. X is plus or minus root 3 halves, or 1 1/2, however you want to write that. Okay, cool. Let's put our second derivative line underneath this one. So this is going to be f double prime, and we'll put 0 here. So 0 is one of my possible inflection points. Can you see that 0 is going to be an inflection point? It kind of almost has to be. Think about making this all smooth here. How would you make this pretty? And not that sharp things aren't pretty, but how would you make it smooth? Let me say that. I don't want to be casting judgment, aspersions on these beautiful graphs, but do you see how it would almost have to change from down to up, concave down to up? So we're just getting affirmations of that. That makes sense, good. Everything's still making sense. And then we've got negative, or root 3 over 2. Oh, shit, I don't know. Can somebody take the square root of 1.5 for me, please? 0.6, I'm going to try to guess. 0.63, I don't know.
1.2.
Yeah, it has to be more than 1. Okay, what I meant was twice what I said. No, I'm just lying now, just making shit up. CYA, all day long. Here, I'm gonna get a nice little chair. All right, so 1.2, was that Olivia, you said that? Yeah, 1.2. So square root of 3 over 2 is approximately 1.2. That's approximately 1.7, so let's say like right here. So there's negative root 3 over 2. Here's positive root 3 over 2. All right, now we have to test the sign of f double prime in these regions. Let's test out here. Test. And you can see it's going to have to be negative. It's got to be negative, my friends. But we'll test it. X equals negative 10. Let's see. Here's what we're using. Using that dude right there as our formula. So when x is negative 10, this is negative. This is positive. Wait. Yeah, so it's negative. So here, f double prime is less than 0 in this whole region right here. And then I test in here. Oh, God. Geez, negative 1 would be easy. Test x equals negative 1. Negative, negative, positive. F double prime is positive. In their test positive 1, we're going to get a negative. Right? So test x equals plus 1. You've got plus, minus. F double prime is less than 0. And then finally, test, x equals positive 10, positive, positive, f prime, f double prime is positive. Okay, so we have some inflection points. We have 3 freaking inflection points. One here, because we go from concave down to concave up, from concave up to concave down, and then back to concave up. So we have 3 inflection points. And those points are going to be at x equals negative root 3/2, 0, and positive root 3/2. And so this means our picture, when I come in to tweak this thing, it's gonna look like this. Let's see. So we're concave down up to here. We become concave up, but we're still decreasing. Oh, look at this. Like this. And then it becomes concave down here, and then concave up. And that is pretty wild. So that's a very sophisticated graph that we ended up with. I wish I could make it a little prettier here, but it gets all the points. Check out all the subtle little bumps and stuff that you never would have got without this deep calculus analysis of the whole thing. Quite lovely. Man, graphing is one of the things that I just loved so much when I was like just graphing for recreation, right? Just like high school. Like if you've done a graph for recreation, you should probably be a math major, right? If any of this is soothing to you, come talk to me. I'll hook you up. Can I answer any questions on that? Because I got one last problem we're going to do before we call it a day. You're going to do.
Can we find f from f prime?
We can. What a freaking awesome question. We're going to be able to do that the last 3 weeks of class, which are coming up soon.
Because I just plugged that into Desmos, and I was like, well, that's not.
Let me show you what the actual graph looks like. So, if you've had calculus before, basically what we need to do is differentiate backwards, Alex. So here's a little preview of what's to come. This would have come from an x to the 5th thing,
Yeah.
right? So if I took the derivative of that, I get that.
Yeah.
So f itself equals, and then here that would have had to have been an x cubed, so I would have had a 3 out in front. Notice how the derivative of that is that, and then plus a constant.
Okay.
So if you actually just graph that guy right there, I think that will actually be what we have. I gotta see.
We'll see.
I gotta see. This is exciting.
3x cubed, and I'll just do plus 5. Yeah.
Sure. Looks good, doesn't it?
Sure.
Looks good. Here, can I show everybody?
Yeah, I don't care.
Can you zoom it a little bit? Can you like scale it so that it looks closer to what I made? Just
A little
like that.
like that.
Oh yeah.
Let's see.
Yeah, pull back, pull back. Thank you. I'm gonna carry this around and show everybody. But, see?
Yep.
Yep.
So excited.
I am excited. It's, yeah,
Yeah.
good. Yeah, because it's fucking amazing. Indeed, yes. Everybody, I love how everybody's like pretend like, yes, yes, thank you for showing me. You're all so kind and polite. Look, we did what the computer did. We're as smart as the computer. We're smarter. Computer just plotting a bunch of freaking points. Computer don't know shit.
Computer can do it faster though.
Computer can do it faster, but not with as much finesse and elegance.
As a marker.
Computer's just cranking shit out. All right, so last problem for today. I'm gonna give you F this time. And I want you to do a number of things. I'll give you a list. So here, suppose f of x equals 2 plus 3 over 1 plus x plus 1 quantity squared. Oh,
That looks gross.
oh no, what? Say things like that. So, what I would like And let's do this together so that we're all sane. We keep our sanity as we venture into the darkness. Step one is find f prime. How about let's not find f double prime. I don't think you're going to be happy with me if we do that. Let's just find f prime. And you might want to simplify. Yes, sir.
Use the rule.
Yes, quotient rule indeed.
Just making sure.
No, I'm glad you're checking. Yeah, quotient rule is definitely the way to go. And then, if you get that done before we go through it, rock it out, see if you can get a graph. Get the critical values, classify. There's a couple ways to do it, Alex. Yeah, quotient rule is certainly not bad at all. You do get that 0 from the top derivative, right? But it's okay.
Can you also bring the whole bar quality up to a negative?
That would have probably been, yeah, that would have been a nice way to do it, Callie. Yeah, absolutely, like this. Like that, yeah. Is that what you were thinking?
Mhm.
Yeah. And then chain rule it. Yep. So first derivative probably should look just like that. After some simplification. I'm actually gonna crank out the second derivative on my own, and then we can compare, and whoever wants to join me can, but you can use this information now to get a very nice graph. I would also consider what is the limit as x goes to infinity, and limit as x goes to negative infinity, and that would give you some really important information as well. That seems weird, but okay. Hate it. Okay. All right, let's join back up. Any questions on that first derivative? We good on that? So, the bottom is a little tricky. The bottom here is something we should think about, but it actually can't ever be zero. Look at the bottom. It's 1 plus something squared. The something squared is always positive no matter what that thing is. And then, well, I mean, hell, then we even square it again, right? So this bottom can't be less than 1. So notice that the denominator, and you don't have to understand that, but it's good to understand that that denominator is always greater than 1. It's bounded away from 0. So we don't have to worry about that, and really the only place we can go to 0 is on top. So f prime of x equals 0 when the top equals 0. Notice how I'm always breaking these things down into smaller problems. Every time, that's how we do it. And that only happens when x equals -1. So at -1, we got something going on. Let's do a derivative chart. So here's f prime. Here's -1. If you care at all about the second derivative stuff I did, I'll hobble over here. -1's right in here. And you see you've got nice symmetry in terms of the concavity around there, but you don't have to see that, and that's okay too. All right, so f prime, I'm going to test x equals -10. Bottom's always positive. The top is now negative times a negative. So here we have f prime greater than 0. We are increasing.
Wait, I have a question.
Yes?
You always do the numerator instead of the denominator when putting in like the zero? That makes sense?
Yes, so when I want to find where it equals 0,
Okay.
I just look at the numerator.
Okay, so we don't have to.
Don't even worry about the denominator. And if the denominator could be 0, then that would be a separate problem we'd have to figure out. Good news is here it can't.
Okay.
So, but yeah. Yes, ma'am. So we're at positive here, and then I'm going to test x equals +10. Look, the top is going to be negative. The bottom's positive. So here we have f prime positive. So, oh, whoa. Slow down, dude. Negative. -6 times 11 is a negative number. So the graph must be going up and then down. Okay. Let's look at some other things. What are these limits? Did anybody crank these out? What's the limit as x goes to infinity? What? The part of it's 0. This part is 0. Yeah, so as x gets bigger and bigger, this dies, because it's a fixed thing over something blowing up. So this piece goes to 0, but then we have 2 plus 0. So this limit is 2. And actually the limit, as x goes to negative infinity, which I should have written here, is also 2, because when x is a negative a billion, this is 3 over a big number. It's almost 0. This limit is also 2. So this means something really weird is happening here. Let's see. Here. So here's my graph. I know that I approach 2 as x goes that way and x goes that way. Notice that this thing can't even be less than 2 either. Look at the original function. Positive, positive, positive. 2 plus a positive number always. That means this graph lives above 2. So it's something like this. Now check it out. At -1 we had a max. So it must be asymptotic and then come down like this. Because it was decreasing on this side, increasing on this side. Does that match with my concavity info? You bet your butt it does. If I just did it better. So concave down, concave up. And this would be -1 minus square root of 1 over 3. And this would be -1 plus square root of 1 over 3. Now we got a really beautiful graph of that thing. That's all she wrote.
Desmos concurs.
What's that?
Desmos concurs. The max limit is 5 though. Like the top of that.
Oh, that sounds right. Yeah, so let's see. When x is -1, we've got 2 plus 3 over 1. So perfect. Now let's label it. Thank you.
But it's,
What's that?
it looks a little sharper in this one. But
It's a
just
little
because of scale.
Yeah, it's scale and less finesse. All right, my friends, that's it. That's a little early today, but I understand. That's enough for one day. We will meet in person on Friday in our room, 11. See you then. Shoot me an email to just remember to extend the link work for you.
Yes.
And then so we can set up when you're free on your
Thank
first.
you.
Thank you.
Thank you.
Thank you. To 12:30?
Yeah.
Okay. Cool. I won't have long, but we can just maybe touch base for like a half hour or so.
Okay.
Sound good?
Yeah, thank you.
Awesome.
For sure. Yeah, for sure. So,
Oh, it's the same Zoom we always use. It's the 6406. It's the one that I keep posting, but, so you tried to be there and you couldn't. Okay, I'll send it out again.
Okay.
We'll make sure you get there, Wally,
Okay.
okay? But we're not meeting in
Yeah,
Zoom
we're
this-
meeting.
Yeah, okay.
Okay.
Did you turn off your recording?
I did not.
Okay, I got.
Thank you.
Let me press the button on that.